is that you have a homework set due on Monday. I am going to try and get another homework set started tomorrow. And I don't want that to be like a big freak out, but you do have an exam coming up, and I would like to do a little bit of practice with thermal resistances. I think that is review for many of you, but just to make sure that you're feeling good about it, I would like to give you a couple problems on that. It might have some other problems that are newer stuff, but I'll try and be clear of what things I think you should have worked and feel good about before the exam. So again, this homework set will come out, and it could be have some that I would like you to definitely have worked before the exam, and that would be resistance network. And then some I'll let you know if it's not due before the exam, those you'll have another day or two to finish up. Okay, and I haven't figured out exactly when it's due. I'll think about how long it is and figure that out tomorrow. Okay, so a recap of what we were doing. And I don't know if I told you guys, I never cover fins in the undergraduate class, so it's bad, but we're gonna spend a little time on fins now. We're looking at this one-dimensional fin. We talk about having X conduction only, steady state, constant properties, no volumetric heat generation. And we started setting up this equation. We did an energy balance. Okay, keep going. We had gotten kind of reduced, condensed down to this form of the equation last time. Okay. And I said we were very close to writing down a solution. Okay, before I do that, so let's leave this for a minute. We're going to write down, and we want a solution for theta, which is our non-dimensional temperature. We end up doing a lot of non-dimensional work in the kind of near future, and you'll get used to trying to think of theta now. If I can solve for theta, I know what my temperature is. We want to make another adjustment to this equation, and we're going to set so we're going to say m is equal to the square root of this quantity. So our equation now looks like all right. Now is when we think back on differential equations, and this ordinary differential equation has a solution of the form Okay, and I have in my notes, because I don't do this all the time. I don't look for solutions to differential equations, but just how you would check. I would take the second derivative of this equation and plunk it into this equation we derived up here. And then I have theta. I put this form in. I should end up with a result that it's back to 0 to check that that is a valid solution. And indeed, that works. We need two boundary conditions now. Okay. The two boundary conditions we're going to use are at the base of the fin. Okay, and I draw up these fin pictures all the time, but maybe indulge me for a minute more. You know, we could think of this as a circular fin. It can be a flat fin. I'm just showing the pieces I would like that you think about are that it has uniform cross section, and that where it's attached to the wall, we make that x equals 0. And we're going to say that it's in perfect thermal contact so that the temperature of the base of the fin is the same as the temperature of the wall. And we usually assume that we know that. That's something given. Okay. But I'm not working with temperature anymore. I'm working with my independent variable is now theta. So it says, and I really want to write this as theta, still at x equals 0. And now theta is defined as temperature minus free stream temperature. Do we have that up here? Yeah. Okay, so temperature minus T infinity, but the temperature we're interested in is space temperature. The notation is that we end up calling that theta B. In this chart that's coming up, that I keep pushing down, so we haven't gotten to see it yet, you're going to see that there's actually a few different boundary conditions I can select for the second boundary condition. And there's 4 different ones shown in that chart. We'll look at it in just a minute. The one that I picked to look at is, we're going to say I have convection going on at the tip of the fin. In these fin problems, and I'll probably say it again once we get to that chart, you always pick boundary condition 1. That's used in every one of the solutions we see in that chart. But it's this boundary condition at the tip that changes to get different solutions. Okay, so what did I write there? This to me looks like Q convection is equal to Q conduction. Okay. So the heat that is convected away from the fin had to be conducted to the tip of the fin. Okay. And L, I haven't shown this yet, that's kind of our standard variable we're going to use for the length of the fin. So how far it extends in the x direction. Okay, but we just saw above that we're not working with temperatures, we're working with, oh, and it's not a non-dimensional temperature. It is a redefined temperature. It still has dimensions. So this guy, we're going to call theta L. So normally it's a temperature minus T infinity, but since it's a temperature at the tip, we're going to call it a theta L. Okay, and this is a dt dx. We're looking at how the slope of that temperature right at this tip varies. So theta L at the end of the, as a function of x. Okay, so those are our two boundary conditions. Now we're going to apply them. Okay. Okay, so the first one we're applying relates to this first boundary condition at the base of the fin. So we're looking at this temperature difference theta. So it's theta B at the base. And then I want to write out this equation C1 E M X. But I want to remind myself that we're looking at this location at x equals 0. So this x really goes to 0. And so it means that exponent is 1. Not the exponent is 1, but e raised to the 0 is 1. Okay.
Professor Brehop?
Yes?
Sorry to interrupt. Are you recording this lecture?
No. But and the fact that you answered means I'm sharing it, so hopefully everybody's hearing it.
Yes, we're hearing it. I just wanted to, there was a message from somebody who was having trouble joining. I just realized she would probably benefit from a recording if you want to do that for this lecture.
Okay. Okay. Okay, I think I've done it. Okay.
Looks like the little recording icon is on. Thank you.
Oh, okay. Ooh, but now I'm having some other issues here. All right, sorry about that. Hopefully I'm getting back on track. Okay. Okay. So this result tells us, what does it tell us? Okay. So I can't solve for one of them, but we're, again, imagining we know what that base temperature is. So this is really a known, and we have these two unknowns, C1 and C2. Okay, so the second one, so that's this equation over here that we came up with. So I'm rewriting H, and theta L means I would take my expression, I can just get it back on the screen, for theta, but now I'm going to make x equal to L. So C1 e to the m, and now x is going to be L. Okay. I have to take the derivative of this theta expression now. And it means I end up with, I'm taking an m out in front. So I have an m C1 e to the mx. But again, x, we're looking at x equals L. And then I get a minus m from taking the derivative of that second term. All right, and there's not much simplification I can make to this one. So I'm going to leave it in that form. The point here is I have this equation, and maybe you're not thinking through, but I know all of these guys. I'm going to know M, and we define that up above. It's a heat transfer coefficient, a perimeter, cross-sectional area, and thermal conductivity. So all things that we should be given for that fin. So I have two equations and two unknowns. And I'm going to tell you, it's not trivial to work to what these two constants are, these C1 and C2. I haven't done it. I haven't come up with the solution. So I'm going to tell you, it takes some time, and I'm not showing it. I am going to write down, or at least show you what this final equation looks like. So we're picturing, now I should have theta in terms of, these constants, and I got e to the mx and e to the minus mx, and the solution is this one here. Oh, okay, and what we did, we just did the temperature distribution. We solved for theta. Okay. So let me get you oriented to this table for a minute. This says temperature distribution and heat loss for fins of uniform cross section. So you remember the other day that we said the fins, as it moves in the x direction, it's not increasing or decreasing in cross-sectional area. We're going to do that situation a little bit later. But for right now, uniform cross section. And then I said, we're always going to have two boundary conditions that we need. We always assume the base temperature is the temperature of the base, but we have a couple options for what we do for a boundary condition at the tip of the fin. And we just did this one, convection heat transfer, and they show what the boundary condition looks like. We also have adiabatic boundary at the tip. We have a prescribed temperature at the tip, and we have an infinite fin. So infinite fin says it gets so long that we have T infinity at the tip of the fin. And if you think about this, so this is T minus T infinity. And so the fin gets so long that the temperature at the tip of the fin is back to T infinity. So it's 0. In practice, the one that we work with most often, if we're not given information, it's most common to assume an adiabatic fin tip. And you can see that the equation doesn't look quite so bad as the case that we came up with. So we may do work with these other cases. We end up doing more with adiabatic fin tip condition. All right. The temperature distribution, they plot it as theta over theta b because now they're non-dimensionalizing it. So theta over theta b is like the temperature that we want to know. So temperature as a function of x minus T infinity over TB minus T infinity. So you still want to think of, this is the part I want to know. They have just written it in this non-dimensional form. Okay. The next thing you might be thinking of is we have hyperbolic cosine and hyperbolic sine appearing in this equation. And it kind of comes, I don't know, I didn't have any of those in this previous, equations that we looked at. We had these exponential terms, but hyperbolic cosine looks like And not that I think that gets you all the way there to going, oh yeah, I see how that happens. But maybe the fact that I had all of these e to the mx and e to the minus mx, you're kind of seeing how hyperbolic cosine and hyperbolic sine might end up in this equation. So one more thing, I end up following how our table is shown here, but I would like you thinking that we're taking hyperbolic cosine of all of this stuff. M times L minus X, and then you operate on that combination of terms. They keep M out because I think it makes it look a little bit neater, but so I haven't shown you how we got to that result, but it does come out of solving for the C's, and you do a lot of rework and you get to this temperature distribution. Okay, one more thing we want to try is we're going to see if we can come up with thin heat transfer rate, and it's got a little Q subscript F. So I've drawn my fin again. A way that we can solve for the heat transfer rate for the fin is to picture taking a slice right here at x equals 0. And thinking about any heat that is conducted from the base material through the fin is eventually dissipated by the fin. You know, if you think of taking a cut someplace else and figuring out what's conducted through, you already had some heat convected away that you wouldn't be accounting for. But if I take my slice right at that base of the fin and calculate what's Fourier's law of conduction, what has conducted into the fin, that should give me what is heat removed by the fin. All right, and just because I'm scrolling down, I guess I already wrote it, but here's the definitions for hyperbolic functions. Oh, we're coming up with having to do some derivatives of hyperbolic sine and hyperbolic cosine. You know, the other thing, I never remember all of these, the form of hyperbolic sine and hyperbolic cosine, but tangent, hyperbolic tangent, it has limits. It goes from -1 to 1. And we're going to see hyperbolic tangent up here. And I always think it's kind of interesting because you'll see, you know, physically it's a value that shouldn't go above 1. We look at ratios and there's a reason it wouldn't be greater than 1. And indeed that curve shows it has a range. It goes to -1, but for our physical systems, you know, we're looking at actual systems that are transferring heat, we're only going to be working from the 0 up to 1. Okay, so back to this guy. And I'm going to look at this part for a minute. So we want to take the derivative of this temperature distribution that we have shown for this convection off the tip. Oh, yeah. Let's do one more thing. Okay, and then I want to remind us that we're looking at right at the base, x equals 0. All right, and I'm scrolling up just for a minute. All I wanted to show is this is equal to theta over theta b. So I want to take theta b to the other side, and everything else in that equation should look the same if I haven't made any errors. Okay, so theta b, that's just a constant. I'm pulling that guy out front. When I take the derivative of cosine m, and again, it's of this quantity, the ml doesn't give me anything. It's not a function of x, but this minus mx gives me a minus m out in front. Okay. Same thing on the second term that I get. I'm taking the derivative with respect to x. I get a minus m out in front, and then everything else stays the same. And I don't have to do anything to the denominator, just a constant. Right. At this step, I went ahead and put things back together. I had my minus k cross-sectional area. And now I'm back to, I'm putting my d theta dx in there. So that's a theta b. And I took a minus m out of here. So let's do minus m from each of these terms. And now I'm starting to regroup this stuff. All right, I don't know if you're getting tired, but I'm going to say this is the same denominator as above. Okay. But now let's apply the fact that we want to evaluate this at x equals 0. Okay. Gone and gone. This was maybe, I don't know, 20 minutes ago. I don't know how long we've been working on this. We had a definition for M, and it's that it's the square root of HP perimeter and KAC. So I'm going to go ahead and replace this guy. Okay, and I need a minus out in front. Let's say I'm going to go ahead and combine this minus sign and this minus sign and get a plus sign. So I'm putting these two together. Oops, oops, oops. We use squirrely curly brackets. Boy, I don't know why I'm not doing a good job getting my pen to work here. Okay. Okay. And I'm sorry, and this is kind of like a mess at this point, but I need to go back and fix this, and I am sorry. We talked about this, and I just proceeded onward. I talked about we get this m coefficient. If I take, and where, oh, maybe it's this direction, sorry. If I take the derivative with respect to x of cosine, I get a hyperbolic sine. So when I took the derivative, this needed to be hyperbolic sine, and this needs to be hyperbolic cosine. Okay, and then I carried that mistake down.
No change in the denominator, correct?
Pardon?
There's no change in the denominator. Is that correct?
No,
Okay.
no, because we didn't have to do any. That was all a constant. And I could have pulled it outside of this and okay, so now we've evaluated. Oh, and did I do the same wrong thing? I did the same wrong thing. Okay, because I was getting all excited before, like, oh, we could cancel some things out. We can't. We end up carrying this thing along. We do have a little bit of work we can do with this. Because if you look, we have a KAC, oops, and we have a KAC down here. So this can look like, well, let's just do parentheses here. K, A, C, H, and this P is perimeter to the 1/2, and then I have theta B, and then I have all the same stuff. Okay, and then the last thing is that they have defined this as a capital M. And the part that will maybe give you some confidence that even though I've messed up my sines and cosines, is that I want to scroll up in just a minute. And the equation that they have given, 3.77. Oh, okay. Yeah, I guess I didn't get it quite right. They have M, capital M is square root, and the square root ends after surface area, so HPK, but they lumped theta B into there also, and I did not put it in there. Okay. But let's look at it, and then I'll go back and fix up my equation. So they got a capital M, they defined it down below. Hyperbolic sine ML plus H over MK, hyperbolic cosine of ML. If we go back down and look, we got that that portion of the equation. So let me get rid of this guy, this whole thing, where M equals KAC, heat transfer coefficient, perimeter, 1/2, and theta B is tacked on there. All right, that was a lot of math. Well, you will get to do some problems and do a little bit of work with that. All right, I need to extend a little space in here. We have two measures of performance for fins. One is called fin efficiency. And in words, it is this QF that we just calculated. So how much heat can the fin pull out? And I feel like I scroll around too much, but I like you thinking about that was this heat transfer rate of the fin. And efficiencies you think should be normally something less than 1. And what we divide by is Q fin max. Oh, and actually maybe now this is when I put it in words. So on the top we want actual rate of heat transfer from the fin. And in the bottom, this is going to be the ideal heat transfer rate if the entire fin surface is at the base temperature. If I was going to make a sketch of this, okay. So the base temperature is at x equals 0. And you are imagining temperature is dropping as I move down this fin because I've got some convection that's pulling heat out of that fin. So temperature is dropping and dropping. Okay. That's the actual rate. That's what we're going to calculate. But the lower part says, this is our estimate for the most we could pull out, is that we'll assume the whole thing is at the base temperature. So now we got really good convection. You know, if I kept dropping heat, eventually it gets really close to T infinity, and I'm not pulling any more heat. I'm not convecting heat away because I have such a small driving temperature difference. So the ideal case is to assume everything's at TB. Okay, and if I wrote this again, if this helps you think about it, if we knew the heat transfer coefficient and we knew the fin surface area, we're going to say the whole fin is at TB. And should be a bigger number than what we have in the numerator. I don't know why we did the convection on the tip of the fin, and now I'm using the adiabatic fin tip case, but it's a little bit shorter. If I were going to write down the expression for efficiency, I'm going to go up to that chart we had, and I'm just going to pull the expression for the actual rate of heat transfer from the fin for this adiabatic case. Okay, so it's capital M, and we know the definition for M, hyperbolic tangent of M, the lowercase m, and the length of the fin. I'm expanding out that capital M. And for the denominator, I'm just putting in my expression I had up above, T base minus T infinity. Okay. And you can already see there's a little bit that will cancel out. This is really TB minus T infinity. Okay. For a fin of uniform cross-section, the surface area of the fin is perimeter times length. And this one's easiest, I think, to think of it in terms of a circular cross-section. So I take perimeter as the circumference, and then to get the area, I have to figure out how long that fin is. I want to substitute that into my equation. So I already got rid of the thetas, HP, K, A cross section. Okay. You can see I have a couple terms here that are common now. And so I could combine this, and I could write this as KAC over HP to the 1/2. I still have this 1 over L. And hyperbolic tangent of M, lowercase m times L. Okay, we're going to leave this equation. That's about as much as you can do. You know, I'm messing around showing you some of these simplifications. This is some of the stuff that you're going to have to think through when we do these fin, like how you get to this simplified form is by looking through, can I rewrite, in this case, we're the surface area of the fin, and cancel it with some other terms. Oh, there's really one more I should be showing you. So this was my definition for M. It's actually 1 over M. So this is 1 over ML All right, see how compact that is? Man, I almost forgot that. All right, mathematically, you're maybe not going to see this, but I'm going to write this down and we'll talk about it. As L goes to 0. If that means I have a really short, stubby fin. So this is my fall. And I got this little fat fin sitting on it. Okay, so that's a very small L. Okay. If you went back to the definition for efficiency, and we're thinking it's what the fin really removes divided by if all of the fin surface is at T base. A little stubby fin is pretty close to having all of its surface at the base temperature. So eta, the efficiency, goes to 1. And so maybe that's making you think, well, and rightly so, well, then why do I use fins? If my best is when I have just this little tiny fin, I'm not improving the surface area. It's really that there's a balance. You're willing to go with an efficiency that's lower. It's still like a pretty high efficiency, you know, maybe 80% efficiency to get more surface area. But this is just a mathematical occurrence that, our definition for efficiency is based on this, maximum. And so a really short fin ends up giving us a really high efficiency. Oh, this L goes to infinity. Yeah. All right, so this one is kind of the converse. Now I have this really long fin, and I could have a bunch of area, like maybe way back here, I already got to T infinity. And so the whole rest of this fin surface is doing nothing for me. And it decreases the fin efficiency. The other measure of fin performance is fin effectiveness. All right, I'm just looking. Okay, so that was one. This one is fin effectiveness. And it is given the Greek symbol epsilon. Same thing in the numerator. So the actual rate of heat removal. Ooh, I like to call it Q fin. I think your book does just a QF. I want those to be the same thing. Okay. And then in the denominator is Q no fin. If I was going to draw a picture again, what the Q no fin is saying, now I slice this surface off, and I'm going to figure out how much heat is rate of heat removal from just that little cross-sectional area of the base surface. If I write my equation in just a minute, I think it will make more sense too. Okay. So I'm in words writing And in the denominator, heat transfer rate from the base area. We're going to do a little bit more work with this. So I substituted in actual rate of heat transfer from the fin. If I used my definition that we just had up above for fin efficiency, it's efficiency, where is it, times Q fin max. So the actual heat transfer rate, so this QF is eta times the maximum fin heat removal rate. Okay. And then heat transfer rate from the base area, that would be a heat transfer coefficient. This is area of the base. And again, you're picturing I sliced off the fin. So if I had a circular fin, my base area is just that area where the fin was. And it's at the base temperature. So the temperature difference is T base minus T infinity. And you can see that there's some things I can cancel out. And this gives us kind of a nice result that it's fin efficiency times area of the fin divided by the base area. All right. Can you think about this ratio of fin area over base area? Is that likely to be a value greater than 1? And you guys maybe don't have your mics turned on and we're getting late in the day. But I'd like you imagining, again, this base area should likely be pretty small relative to all of this finned area. Okay, so it's likely that that ratio is greater than 1. Eta, we don't know how efficient the fin is, but effectiveness is generally greater than 1. And you wouldn't want to use a fin unless you had an effectiveness that is greater than 2. That's in practice. You wouldn't pay to put a fin on if you're not doing much better than just this surface without a fin. And in some of the problems we work, you're going to have fin effectiveness that it's like 12 or 14. So it can be some ratios much higher than 1. Okay, so let's do the same thing we did up above. Let's play with it in terms of the adiabatic fin tip case. And we saw this equation for an adiabatic fin tip. It's theta b this combination of 4 variables and then square root, and then we have hyperbolic tangent m, which has many of those same things, HP and K and AC, and then the length of the fin. And in the bottom, we've already written that before. H, area of the base, T base minus T infinity. Okay. We can get rid of that temperature. Okay, and one more thing. Since our fins are assumed to be uniform cross-section, any place we make the chop, we're saying here we're cutting it off at the base, but if we, all throughout, cross-sectional area is equal to the area of the base. So we are going to do a little bit of readjustment again. So I'm going to have PK, but now I have an h to the 1/2 divided by an h, and in cross-sectional area over to the 1/2 over cross-sectional area. So I can rewrite that as PK over HAC to the 1/2 and tangent ML, hyperbolic tangent. Okay, so that's only for one specific case, the adiabatic fin tip. Okay, so we have this problem coming up that was going to be to calculate fin efficiency, effectiveness, find the temperature at the tip of the fin, and heat removed by the fin per unit width. So a few things that we want to do. And let's start. A lot of these equations are going to involve this m. Let's just start by solving for m, and then we'll substitute it into this equation. I don't think that we're going to get all the way through this problem, and I feel bad, but I'm stalling a little bit. But let's do this one bit. We'll have it set up, and when we attack this next time, we'll have that done. So let's see. Let's write some assumptions. It says a longitudinal fin, and maybe I can make that sketch. Okay. And we got a length. So that's our x direction. That's x. The thickness is 9.5 millimeters. Okay. They don't specify a width. And when they say this longitudinal fin, we're going to end up looking at, it's going to be a heat removal rate per unit width. So I'm going to go ahead and put a W in here, but you'll know that's kind of a placeholder. We're going to end up having to get rid of that because we're going to look at it per unit width. Okay, but I could write my L in here. All right, so what else does it tell me? Exposed to surroundings at 50 degrees C, so T infinity. We got a heat transfer coefficient of 50.2 watts per meter squared Kelvin. The temperature at the base of the fin is 90 degrees C. So we're thinking, we know a temperature here. And we know thermal conductivity. All right, and I said I'm not going to go through the whole problem today, but let's just do M. We can at least get that set up. Okay, I'm scrolling around one more time. We have so many versions. Okay, up here, what is that? PK over HAC. All right. So I always have to look. I'm not, there's not one that we see over and over. So if in doubt, I'd go back up here and I say m squared is HP over KAC. Okay. So I feel okay about that. And then I'm going to rewrite this as H, heat transfer coefficient, and that's given. Perimeter. So I'm thinking about perimeter is 2 times the width plus the thickness. So sort of this. Okay. And I could really think about it any place. It doesn't have to be on the tip of the fin. It's the same all the way through. And K, and then cross-sectional area. So we're thinking about the area we're conducting heat through is going to be thickness times W. The and then 1/2. The approximation that we make is that these fins are pretty thin. So when I look at this width, we haven't said how long it is, but you're imagining it's much longer than 9.5 millimeters, the thickness. So in comparison, when I'm adding these two up, the thickness is about 0. And then
Quick
the next
question.
thing I can do, yep.
So since there isn't any definition of width, how can we assume that it's so much larger than the thickness?
Okay, so we got this longitudinal fin, and they're trying to give us this idea that it's quite long. I've sketched it with a finite width, but really, I'm telling you it is. You'll see problems,
Okay.
and it's not. We'll see ones that are little, rectangular shapes, or we'll see little pin fins. Okay, but this longitudinal fin, we could put this as our assumption. Width is much greater. Oops, I went
Is that just
the wrong
part of the
way.
definition of longitudinal here?
Um,
Part of how
well,
we imagine these fins to be?
it is. And I'm trying to think, the day that we looked at the first slide, and it had the motorcycle engine, and it had these flat fins. That's kind of the idea of a longitudinal fin, that it is much longer in the width direction than the thickness.
Okay, that makes sense.
And now, okay, but we're not dropping it here because the T times the W, now that does have an effect. I mean, if I add up width and thickness, if thickness is super tiny, it's just off on these small decimals. But multiplying the two together, I can't just drop it off there. Okay. But now I can say, and maybe I'll use a different color. I can cancel these two widths, and I'm left with H divided by KT. Oh, and then square root. Okay, could substitute numbers in, and I know I'm ending early, but we're going to do it. So that's as far as we're going to get. We'll crank through this problem in no time flat on Monday. Okay, and I promised you a homework set with thermal resistances at least sometime tomorrow. Okay, I'll hang out for a minute and see if there are questions, and otherwise that ends what I was going to cover for today.
Thank you.